Okay.
Hey, let's record.
I haven't. Well, go ahead. What's up?
What?
Okay. So in this video, we're going to look at doing some of the math associated with collision theory. So if we look at our reaction graph, we've seen the reaction graphs before, where we start with reactants on the left side, we have potential energy along the y-axis, and our reaction progression along the x-axis. As our reactants turn into products going through the activated complex, we can see an increase in the energy leading up to the activated complex, and then energy being released as it moves down toward products. So the amount of energy needed to get to the activated complex from the reactants is the activation energy of the forward reaction. If we were going to start on the product side, the energy needed to get from the product energy to the activated complex is the activation energy of the reverse process. Alright, so remember we can have two activation energies, one for the forward and one for the reverse. In this case, the forward activation energy is much greater than the reverse, indicating that this is an endothermic process. We're putting more energy in than is coming out. Alright, we can also calculate the delta H for the reaction by looking at the difference between the energy of our initial position, or our reactants, and the energy of our products. So C here is the label for the delta H for the reaction. And when we have a scale, we can calculate the energy for each of these. Alright, so our A, or our activation energy of the forward, is going to be equal to our 400 minus our 100, which is where we started. So our activation energy of the forward is 300, probably kilojoules. Alright, let's look at part B. So our activation energy of the reverse is going to be just between the products and the top of the peak. So we're going to subtract 400 minus 300 to get 100 kilojoules for the activation energy of the reverse. Now we can take these two activation energies to find delta H. Activation energy of the forward minus activation energy of the reverse is equal to our delta H value. Alright, so our activation energy of the forward was 300, of the reverse was 100, so our delta H is going to be 200. Alright, and we can see that when we look at the graph as well. Going from this point where the products are down to where our initial reactants were, we have 300 minus 100. Alright, so that would be our delta H. Now even if we don't have a graph, we can also calculate this information. Activation energy of the forward is 110 kilojoules. Delta H is 92. Draw an energy graph for the reaction and find activation energy of the reverse. Alright, so first I'm going to do it without the graph. So we have activation energy of the forward minus activation energy of the reverse is equal to delta H. Alright, so now let's fill in what we have to solve for our value that we're missing. So we're given the activation energy of the forward is 110 kilojoules. And we're given our delta H is 92. So I can fill that in. Now we just have one variable, our activation energy of the reverse. So if I subtract my 110, negative activation energy of the reverse is equal to 92 minus 110. So my activation energy of the reverse is going to be 18 kilojoules. Alright, so if we look at this with a graph, we can get the same information. So I'm going to draw my graph. We have energy on the y-axis. This is going to be my progression on the x-axis. So I'm going to start with my energy of my reactants. And it doesn't really matter where. I'm going to start here. I'm going to say this is my reactants. Then I have activation energy of 110. So we're going to draw a point, top of this peak, going down here is going to be 110 kilojoules. Alright, and then it says the delta H for the reaction is 92. Notice it's positive, so that means it's going to be an endothermic reaction. And it also means that, considering this is 110 and delta H is 92, this is not going to go down very far. So we're going to put it here and call this my products. So from here to this line with my reactants is going to be my 92, or my delta H. And I'm looking for my activation energy of the reverse, which would be from here to the top. Alright, and that's their value. So we can see from the picture that it's going to be a small number for our activation energy of the reverse. And we can do our calculation with our equation like we did here. Or if we had a scale that had numbers, we could calculate it that way. Either way, we can see that it's going to be 110 minus 92, because here's our 110 value, here's our 92, we need this part, which gives us a difference of 18 kilojoules for our activation energy of the reverse. Alright, so the next math idea we're going to look at deals with the Arrhenius equation. The Arrhenius equation describes the rate constant K. And from the previous video, we know that the rate constant K is based on temperature and activation energy. Okay, and if you remember, we even had an equation for K that was A times E to the negative activation energy over RT. Alright, and remember K is two components. A is our frequency factor, and the rest of this is our fraction of molecules that have sufficient energy to make product. Since this would be an exponential graph, we want to work with straight line graphs. Taking the natural log of both sides gives us this arrangement of the Arrhenius equation. So same information, just put into a linear format. So this matches y for our ln of k, our ln of A is going to be our y-intercept, and then activation energy over R is going to be m, and our x is the 1 over t. Alright, So if we look at a graph using this kind of arrangement for the Arrhenius equation, we can calculate values for our activation energy as well as our frequency factor A. So looking at this graph here, I have ln of k as my y, 1 over t is my x. So the slope of this line should equal negative activation energy over r. And remember, r is our gas constant, so we know what that is. And our y-intercept should equal our ln of a. Alright, so by picking 2 points on the line, I can calculate a slope. And by determining the y-intercept, I can calculate a. Alright, so let's start with the slope part. So there's a couple of points already picked out for us, but it doesn't matter which points you want to pick. So I'm going to pick this one. That one looks pretty close. Alright, so we're going to go our change in y over change in x. So this is negative 10. And we're going to say that's 0.00215. And then a second point. I'll try for this one because I can at least see the bottom part. 0.00195 for my x. And it looks like negative 6.6 for my y. Alright. So we're going to calculate slope. Negative 10 plus 6.6 divided by change in x gives us negative 17,000. Alright, for our slope. So that's going to be equal to our negative activation energy over r. So let's plug this in. Trying to find activation energy, I'm going to use my R value. So energy units, activation energy is measured in our joules or our kilojoules. And it doesn't matter what we pick for R, just remember that's going to indicate what our units are. Alright, so multiply this by R, and we get positive 141,338, and this would be joules. Alright, so that would be the slope of our line, or sorry, that would be the activation energy that we got from the slope of our line. And once we have the slope, we can use that value to find the ln of A. So now I'm just going to pick a point on the line, and it doesn't matter which one. So let's pick this other one down here that looks like it might be easy to figure out. Right, and I'm going to fill in my values. So my y is going to be negative 10.5. Alright, I now have my slope, which was negative 17,000. My x value for this one (0.00215) plus ln of A. Alright, so now we're just solving for the ln of A. So negative 10.5 minus our negative 17,000 times 0.00215. Alright, that gives us 26.05. and that's equal to our ln of a. And then we get rid of the natural log with base e. So a is e raised to the 26.05. Alright, so I get 2.05 times 10 to the 11. Alright, for my a value. And remember, a is our frequency factor. So our probability of getting a good collision times the number of total collisions. So frequently a is a large number. Alright, so let's do another example with that same idea. Alright, we have a new graph. We want to find the slope, so we can find the activation energy, and we want to find the value of A. Alright, so the first thing we're going to find is our slope. So our slope is going to be our negative activation energy over R. So we need to pick 2 points. So we want to find some points that are going to make it easy on us. So I'm going to pick this one. And maybe this one. Alright. So over here, our slope is 6 minus, we're going to say this is 3.4 over 0.2 minus 0.6. Alright, and this is equal to our negative activation energy over our 8.314. So 6 minus 3.4 divided by 0.2 minus 0.6 gives us negative 6.5. Alright, and then we just have to multiply over. So activation energy times 8.314. Two negatives cancel out, so we have 54.0, and this would be joules. Alright, so that would be our activation energy. Then once we have our activation energy, trying to find where our y-intercept would be, we want to plug that in using one of the other points. So remember, y equals mx plus b. We can find b if we know the rest of it. Alright, so I'm just going to pick another point on this graph. I'll pick this one. Alright, so the y would be approximately, we'll call that 4.8. We calculated our slope to be negative 6.5. Our x value is 0.4. And we're trying to find b. Well, let's just write it as ln of a. That'll make it easier for us to remember. Alright, so our 4.8 minus negative 6.5 times 0.4, 7.4 equals ln of a. So remember, we want to do e to both sides. So 1636. Alright, so no problem. Use the slope to find the activation energy. Then we can find the y-intercept to get the value of a. Now, although that gave us a linear form for the Arrhenius equation, the most common form of this actually should look pretty familiar, and that's this form. Ln of rate constant K2 over rate constant K1 is equal to negative activation energy over R times difference in temperatures. Alright, this is similar to Clausius Clapeyron. Instead of having delta H, we have activation energy. Instead of pressures, these are rate constants. But the math works out very similarly. Alright, so if we're given a rate constant at a particular time, we can find the rate constant at a new time. Alright, so we're just filling in the math. So ln, we're finding the new k, so I'm going to call that k2. We're going to put the original k1 in here. Negative activation energy. Since I'm using joules, I'm going to use 8.314 for my R, times 1 over T2 is going to be the 1000 degrees Celsius, which we want to turn to Kelvin, minus the temperature at the first K1 was 10 degrees Celsius, which is 283 in Kelvin. Alright. So we have negative 75,000 divided 8.314, so negative 9,020.9, and then we'll find our difference in our temperatures. Okay, 002748. Alright, so multiply that times our negative 9,020. Okay, 24.789. 6. Alright, so taking e to both sides, we'll get rid of the ln. This is going to be a very large number. Yeah, 5.83 times 10 to the 10. And then multiplying by the 0.126 gives us 7.35 times 10 to the 9. Alright, so we have a very large K2 because we have such a dramatic increase in temperature. Remember, increasing temperature is going to increase our rate of reaction because K is going to increase. Going from 10 degrees Celsius to 1,000 is a large jump in temperature, so we're going to see a huge jump in K. Now the second question was, what is the reaction order? And this we're going to look for the units of K. So our K units were liters over moles per second, which is the same as 1 over molarity times second, so this is second order. And we're going to have the same units for the new K value that we found. Alright, then our last question, our concept question, is K always going to increase when T increases? So as our temperature goes up, we will always see an increase in K, because we're going to have increased kinetic energy of our collisions, we're going to have moving particles that are going faster, so that's always going to increase our rate of reaction by increasing the K value. Right, and the last part of this is just the summary of all the equations that we've looked at for this part. Alright, so we have our fraction of molecules that have sufficient energy. We have our frequency factor being the number of collisions times the probability of a good collision. Arrhenius equation. Alright, and then the form of the Arrhenius equation that allows us to calculate K at a different temperature. So make sure you understand each of these equations and how to use them.